All right. Yeah, we can begin now, please.
Yeah. So once again, good morning to all of you. It is my distinct honor to introduce our esteemed speaker, Professor Sourish Das, who is currently serving an associate professor in the Department of Mathematics at Chennai Mathematical Institute, India. So we are very lucky to have sir with us today. So a warm welcome to you, sir.
Thank
So
you.
now I would like to invite sir to deliver his talk entitled Predictive Modeling with Julia. So sir, over to you.
Thank you very much. So before I start, I just want to tell you a couple of things that I mean, most of the time I um, use, so I'm more fluent with R language and Python effectively. So Julia is more recent, interest, I would say. And I'm not saying those of you are kind of learning R, Python, and I'm not saying that no, you give up on your R, Python, and start Julia. I'm saying in addition, you can learn Julia or at least have some familiarity with Julia. Technically, if you, as a user perspective, it works pretty much like R, Python, or MATLAB and some mishmash of like syntactically and all these things. In addition, it has certain advantage of advantage as a programming language because it came new. It is newer language. So when they designed the language, they more thoughtfully designed it and made it much more useful. At the same time, for certain use, it is certain kind of work you want to do, probably it will not be at mature. For example, if you want to say run a deep learning module, right? And it will not be as mature as Python. Okay, any deep learning module will be way more mature in Python because, for 10, 20, 15 years, people are working, like thousands of people are working and contributing in those packages. Big companies like Facebook, Meta, they are contributing in those packages. Those packages have become very stable and robust, and it is very difficult to come up with any other package or any other language which will be as good or as mature as those um, languages or those packages. So it will not be, if you want to, if you're using deep learning model, so I would say, okay, you stick to that. Then where should I use Julia? And that is where my stake is, that one of the advantage of Julia I found is compared to R, Python, or MATLAB is in its design. So R, Python, or MATLAB, these are the three typical language for very popular for scientific computing. These languages are effectively interpreter language. Okay. Whereas if you look into the Julia is not an interpreter language. Julia is a compiler language. That makes a lot of difference. So basically, if you want to, an interpreter language are typically called high level language, and they are not as fast as a compiler language like C. C is a compiler language. So if you really want to make your algorithm very fast, so what people do, they write the function in C and then make a R call or Python call from the Python to that C language. For example, if you say, if you want to run a MCMC, right? Nowadays, one of the very popular package is called Stan. So Stan is a standalone package written in C. And then there is a RStan interface or PyStan interface. Through that, you have to interface the Stan. And then there is a very strict language barrier, and then you have to work through it. So as a user, you have to have your R or Python correct version and the correct version of stand and C. So there is a 3 different language, and their version needs to be correctly aligned to get the correct, the things actually work. So, but it works, then it works very beautiful. It's really works very good. I have used both R stand and Pi stand. It really nice. Com Runtime complexity wise, they're equally good in R and Python. So they're very good. Only problem that I faced during the installation, you have to have a correct version should talking to each other, and that's sometimes very nightmarish during the installation. But uh, if you can overcome the installation part, then you are done pretty much. On the contrary, if you see the Julia, I found Julia is a compiler language. So Julia has its MCMC module called Turing.jl. I will show a little bit on that. And then Julia, all you have to do, install your Julia and package.add Turing, and then you are up and running. Just 2 lines of code installed, done. Because Julia's compiler is written in Julia, the Turing itself is written in Julia. So everything is written in Julia. So everything is in the same ecosystem. There is no different ecosystem which needs to have a correct compiler version and all these things. So you don't have to worry about any of those things. So that is one of the advantage I really found. Julia is fantastic. Another case I found Julia is very useful is because Julia allow Unicode system. So as a result, you can write you can define your variables, or in the way you want. Like if I want to say alpha equal to 5 and beta equal to 6, right? So in a R or Python, I have to write ALPHA equal to 5. And then, but here you can literally write alpha um, as a LaTeX symbol, and then you tab it, and then it will come up as a alpha. And I can show you. Can I share my screen and show you some of the fun stuff in Julia?
Yeah,
Yeah,
sure,
please.
sir.
Okay,
Yes, sure.
let me share my desktop. All right, so here is I have one, I completely wrote everything in Bengali. I have a Jupyter notebook in Julia, and it's everything is written in Bengali. Okay, so like if I run it, and it will run, and it will give me a type of, it works perfectly fine. And then so you can do the addition, subtraction, everything here. My variables are all in Bengali. And so here, even you can handle string, and then you can do the string operations and all these things you can do. So here, I think I put it in a particularly, so I was showing that, okay, if you use toString here, I mean, two quote unquote, it will get a wrong way of doing it. So you have to do it 3 string. If you want a quote unquote, then, so basically what I'm trying to say, let me just run it. So I want to say this particular word to be in the quote unquote. So what you have to do, you have to say 3 string within the 3 string, and then if you do quote unquote, then quote unquote will not be as a string, and it will work out. So, and in fact, you can write your functions also. So here I can write your, loop in the loop variables can be written in your language, whatever language you want, um, and then you can write your function also, like here. Oh, sorry. You can write your function also. So it is says that Namaskar Shomri Kam Shubhat. So now I can write anything. You can write, and it will run pretty much. So you can write, this is something I found that I cannot do in R and Python. So this was for me just a fun. So this is really when I saw these kind of functionality, and you can see here I have given is a ko is a Bengali script. I say ko equal to 2, and kha is another Bengali script, kha equal to 3, and ko plus kha is 5. So you can literally define your variable on your own regional language, and I found that was really fun. And probably this can be introduced at a very even in a government schools, where I studied in a government school, and I studied in my early years in Bengali, and so I got to introduce to computer programming at a very late stage, like masters, during my master's final year. Before that, I never actually got in that sense introduced to. So I knew, okay, here is a computer, and my like my some of my friends were studying computer science in college and all these things, but I really never got introduced seriously as a course in the thing. So, but uh, I think this could be helpful to introduce it to at a much more local level, local language, particularly in the regional areas, in the remote areas, much more be easier to introduce the concept to the, you know, to the children. So please stop me if you have any question or anything. I mean, one of the problem with the, this kind of online thing, I really will not be able to understand if you have any questions. So please stop me anytime if you have any question. Now, so next, what I'm going to do, I'm going to introduce you another reason, because here, few things like, let me go to the same notebook I have in, English also. So I have a series of notebooks to introduce Julia. I can share some of them, and it will be very easy for you guys to understand and start. So let me go to CRRao. That CRRao package, why I I wanted to build this package. Let me tell you honestly, and initially I thought I will do it in R, because that is the language I'm most comfortable with. I did my R PhD work in R, and then still I learned Python in last 10 years when I moved to CMI. And I realized that, some of the things, it is important for the students to learn Python. And so I also started learning Python and implementation of Python. Some of the implementation of Python is very easy. So I thought I will. So I thought either I will do it in R or Python. And then when then the roadblock was essentially the MCMC, because I wanted to do both frequentist and Bayesian uh, predictive models. Okay. Frequentist was very easy. You just call the OLS solution, ordinary least square solution, you are done. Or for some like logistic regression or something like, some say Poisson regression, you call some gradient descent type, Newton-Raphson type algorithm and run it through the optimization procedure, and you are done. But the problem is the Bayesian. The Bayesian, you have to rely on the MCMC. And R and Python relies on essentially RStan, PyStan. Those are the most. PyMC3 is also another very popular, but I'm not that familiar with PyMC3, but mostly RStan, PyStan. And the problem I felt that RStan, PyStan is the one I told that there is a Stan language and then there is a C language. So and your system, all three should talk very seamlessly without having any difficulties. So I found that is bit of a challenging as a developer. And even if I develop one, if in future uh, if somebody wants to contribute in that package, they also have to go through a lot of difficulties. I found it is extremely easy to contribute into the Julia package. It is because everything is in the Julia ecosystem. You install Julia, you install um, your uh, you know VS Code, and it works with VS Code very seamlessly, and you can just develop everything in that environment and you're done. So I that is the reason I found it is much more easy and easy to implement. So first, so in a linear regression, so in this package, total we implemented around 42 different predictive models, different variations of predictive models, out of which 8 of them are linear regression. Linear regression with a simple ordinary least square method that we teach in the classes, linear regression, bootstrap regression method, and then about 6 of them are Bayesian linear regression with a different kind of prior, expert elicited prior, reach prior, Laplace prior, Cauchy prior, T-distributed prior, horseshoe prior. Now, those of us have worked in our Python, we know that all these priors are not in one single environment. They are all in a different packages, and each packages has their own weirdness. So you have to be familiar with each of the packages, and or you have to write a code on your own code and run it on the RStan or PyStan. So this is the main problem that I found in the R and Python. And I found, so here, so what we did, we said that, okay, all you have to do is sort of because I am from R and my colleagues are all mostly they are from R. So we had some in the design thinking, there is a bit of a R and Python in like kind of info things are there. So let me just, instead of giving you Gyan, let me just giving you some demo. So here, simple linear regression has y equal to some alpha plus x beta plus epsilon, and x is the typical covariate vector and y is the response, and epsilon is the white noise or simple error, follow normal distribution with mean 0 and variance sigma square. Y is a response vector of size n, a vector of size n. X is a matrix typically called design matrix of predictor variable of size n cross p. There are p variables, and then n is the sample size, alpha is the intercept, beta is the regression coefficient, and sigma is the standard deviation of white noise. All right. Now, what I'm going to do, let me just okay, let me just first put it here. Let me just run this piece of code. So like Python, you do import these packages. In Julia, you do call the packages by calling it using. So using CRRao, our data set is another package which has some popular R data set is being kind of clubbed and put it into the Julia, released in Julia. And stats model, some of the statistics models we will use in this case. And then from the data sets, these R data sets, I'm just calling the, so from the R, there is a package called data sets. In that data set package, there is a particular data set called empty cards. I'm calling that particular data set. So if you run this, just a minute. Okay, so this is the data set. So miles per gallon, it's a different, about 32 variables are the rows are there, instances are there, and different, each row represents a different kind of model variant. And MPG stands for miles per gallon, the fuel efficiency, and these from cylinder, dispersion, horsepower, rear axle ratio, weight, these are the different feature of the car. Okay, so given these features, we want to say miles per gallon, something about the miles per gallon. So here I'm not going to use all the variables, but I'm going to use horsepower, weight, and gear. So the model will be effectively like effectively like miles per gallon equal to beta naught plus beta 1 times HP plus beta 2 times weight plus beta 3 times gear plus epsilon. Okay, if you run this, so this will be our model. All right. Obviously, epsilon follow normal 0 sigma square thing. And what we are doing, we are saying that a formula MPG tilde HP plus weight plus gear. Now, this part you can say that it looks like more like a R kind of thing. And then fit is more kind of Python. You just give a Python kind of thing we have done. And then you have to give the data set name. And then you have to tell what model class you are using. You want to fit like linear regression, or you want a logistic regression, or you want a Poisson regression. So you have to tell the model class. Once you do that, it will fit the OLS method. So OLS model method of fitting the model. So this is a frequentist method. So this fit the model. These are the coefficient. The beta naught is 32.0137 with a standard error of 4.36. T value is basically 32.0137. Divide that by 4.63. You will get approximately 6.91. P value is basically probability that it will be any, if you repeat the process again, a random process, then what is the chance that you will see another T which is greater than 6.9 when this is the P value. Smaller P value means you have like that particular predictor has a effect on the response. Now here you can see gear. Gear has p-value 0.24. Okay, so that means effectively I can say gear does not have an effect on the response miles per gallon. Whereas horsepower and weight, they have p-value 0.0009 and 0008, very small. So that means we can say horsepower and the weight, they have effect on miles per gallon, and they are negative. So it means the horsepower increases, the fuel efficiency goes down, and the weight of the car increases, the fuel efficiency goes down. So that makes sense. Okay. And so, and then if you calculate the sigma, if you want 2.57 is the sigma. So this is the essentially this particular sigma. The epsilon follow normal 0 sigma square. So that sigma we are getting 2.57. Now what we are doing here, next here, we are going to calculate root mean square error. Here I'm doing the in-sample root mean square error. You can do a out of the sample. I'm not going into the detail of training, testing, and splitting and all these things. I'm just showing a demo here. So basically here I'm just saying that in the predict LM model OS, if you don't provide any data set, what it will do, it will just take the training data set and it will calculate them, predict the values on the top of that. And then it will calculate the root mean square error. From the DF, it will take the original value, subtract, square it, take the mean and take the square root. So root mean square error is 2.40. And that is where you would supposed to see that 2.40 and 2.57, they generally should be close to each other. Here I am plotting the Cook's distance, which is essentially measure the if any particular value in your data set, any particular observation or in your data set has a significant effect on your estimation procedure. Turns out these particular observations, 15, 16, 17th observation has the maximum amount of leverage or the influence in the estimation or the training procedure. Now, what is this 16th observation? So it is not being plotted. Let us see this. Let us see this 16th observation. Let me just create a. All right. I want to see 16th observation, comma this. Lincoln Continental. Okay, yes. So this is one of the very not so popular cards. So if I just say 15, I say 15 to 17. Okay. So I can, it will give me 15, 16, 70. Cadillac, Lincoln, Chrysler. And this one, though it is looks like very, very simple. Horsepower is 215. Weight is 5.425. Similar kind of behavior you can see, but some reason it shows that it has a very influential point. It is interestingly, it has a very influential point. Anyway, so these kind of post-mortem analysis you can do with the simple regressions, and this is the actual value of miles per gallon from the OLS and the predicted value of the OLS, miles per gallon, that you can calculate. Now, another one of the criticism typically comes to the OLS method, that we assume this epsilon follow normal 0 sigma square, and not necessarily this error actually follow normal 0 sigma square. They can follow some bell-shaped distribution, but typically different from the normal distribution. And if you don't want to assume normality, one of the way thing is you just use the bootstrap method. So if you look into the previous model, you fit the bootstrap linear regression exactly the same way. You just call the fit formula, provide the formula, provide the data frame exactly the same way. If you look into the previous one, this is the exactly same way. Okay. Let me just put it there. I'm fitting it exactly same way, up to linear regression exactly same way. But now I don't want OLS. Default is OLS. I don't want OLS. I provide bootstrap the residual ones. So it will do the residual bootstrapping. Okay. So if I run this, so it gives me the OLS estimates with the standard error calculating from the bootstrap methods and the 95% confidence interval for all of these cases. And you can see that Gear is again not effective. 95% confidence interval includes 0 because lower bound is negative 0.23 and upper bound is 2.28. So it includes 0. So that means 0 is a possible true value for the coefficient of gear. So that means gear effectively does not have any effect on the miles per gallon, whereas weight and horsepower, they are significantly, below the 0, both of them. So negative coefficient indicate that they have a significant effect. So bootstrap typically their standard error generally not somewhat similar. If you go and check with them, 4.63, 0.009, you can see 4.17 and 0.0093, and on the upper 0.84, 0.85 was the OLS standard error. And here it is 0.78, 0.77. So standard error has reduced actually, and you are not assuming that it is normal. So that is the advantage of using bootstrap method. You have one less assumption. So this is what you can do without any much of the things doing, and just you add this additional thing, bootstrap regression. It is being defined as a class, and then you run it and it is done. Up to this, everybody are you okay? Do you have any question?
Any questions from the audience? No, I think no, you can proceed. Thank you.
Sure. Next, Bayesian linear regression with expert elicited prior. Now, what is that? So what happens in Bayesian, one of the advantage of Bayesian linear regression is you can elicit a prior knowledge of your parameter in your analysis. So for example, effectively, if I say epsilon follow normal 0 sigma square, so I can assume y follow normal mu y sigma square, or here should be a sigma square. Let me just correct it, otherwise it looks different. And should be like this. Yeah. It should be yi follow normal mu I sigma square and mu I follow xi transpose beta. Now, you believe that, okay, generally we don't have any prior. This part is completely in the likelihood model. We just work with these guys. That's it. Okay. We don't know the beta. From the data, we try to estimate beta and sigma. But sometimes you have some information about beta. What you do? So what it does, one possible way the expert elicited, suppose there is an expert who comes and tells you, I know beta is this particular value, beta naught. Okay. So you said, all right, I will put a beta naught to be sort of a guiding prior value. But it is not exact. Beta could deviate from a beta naught a little bit. So beta naught, beta follow normal, some sigma beta naught, and then sigma follow some inverse gamma. Okay. And then that's it. Pretty much you run it through, you define this model, and you run it through the Markov chain Monte Carlo, and you are done pretty much. So here, but any of you have ever run any Markov chain Monte Carlo, you will know that it's sometimes very painful to code all those things. So what we have done here is very simple. All right. So here is the model. Up to this, you have exactly same thing. So the formula, data frame, and then the linear regression. And here you provide a Gauss prior and with beta naught value. So now for intercept, I'm giving 33. That, okay, most likely it is around 33. And the other values are, maybe I'll just give I don't know the other value. So what I will do, I will say, all right, I 0.0, everything is 0.0, near 0.0. Now, if you run this, and I'm saying 10,000 simulation, you run for 10,000 simulation. If you run this, it will take a little bit time. It is started, done. All right. The first thing I will check the R hat values. If the R hat values are all close to 1, that means my model has converged. My MCMC has converged. It's a good news. And then I will look into it. And here is the values. So these are the estimates: 32.49, 0.03, negative 3 point something, and 0.89. So my previous value was, here I actually was trying minus 3.0, and here I was trying 1.0. Now if you run this, okay. So yeah, just a minute. Okay. So now what is happening? So now the estimates are somewhat similar, but because of I am providing this coefficient, a value which is close to probably the guided values. Now my confidence interval for the gear has become sharper, and saying that gear is also has an effect without, because confidence interval become quite sharper now. So this is sometimes in some of the, depending on the domain, in case you want to introduce your expert opinion, you can do these kind of things using Bayesian data analysis. These are sometimes very useful. For example, when you have very less sample, okay, and the expert generally, and for example, in nuclear power industry, you will not have more than 5 to 10 samples. Based on 5 to 10 samples, if you want to do something, then it's very difficult. At that time, Bayesian data analysis becomes very handy, because what happens, people read a lot of articles from, they may be, so some scientists in sitting in India, they may be studying some article published in Germany, and from there they getting, okay, this could be the value, all right. And then another and she may be studying another article where some American scientists have maybe published, okay, in their plant, these values are somewhat in this region. So based on these analysis, based on this analysis, they can have a prior opinion that, okay, based on historical published data, we believe that the values are somewhere in this region. And you can then plug it in. It's not very easy. I would not say it's very easy. Sometimes it's quite difficult. It depends on problem to problem, but you can brought them in. Okay. So this particular effort was on that direction to, Bayesian linear regression with expert elicited prior. Next, so we did the same thing. Here we did a predicted values. These are the actual values of miles per gallon, and these are the predicted values of the miles per gallon. Initially, they are doing pretty good, but as it goes up, it is doing some underestimation. You can see there is a bit of an underestimation is happening, because where it is 25 up to 25, but here it is 30, but they are doing estimating below 30. So yeah, up to 25, they're doing well. above these values are getting like 1, 2, 3, 4, 5, 6. These 6 values on the upper scale are getting somewhat underestimation is happening. Okay. These are the root mean square error. Now, this is Bayesian linear regression with reach prior, where essentially or L2 prior or L2 penalty. And here is the entire model definition that we have given you here. And if you run the same way, instead of linear regression, instead of prior Gauss, I just gave prior reach. And like you have to give a 0.1. If you don't even give this, it will work actually. These are the default setup is this. Okay. This is the default setup. Okay. And then you can see there is a H value. These H values, if you provide, you have to provide this. If you want to play, it is 0.1 is the sort of a default H value. And if you want to run it for 10,000, default is 1,000 simulation. Okay. And if you want to run it for 10,000 simulation, even 10,000 simulation runs very fast and it gives you the estimates somewhere, the things that you want. Similarly, you can do the L1 penalty or the L1 prior. So in this is also known as the lasso penalty or the lasso prior and or Laplace prior. And you can same way you can just give the formula, give the data frame, tell which model class. Instead of linear regression, if you want a logistic regression, just change logistic regression and keep Laplace prior Laplace, it will work. If you want a negative binomial regression, just instead of linear regression here, you just say negative binomial regression and then prior Laplace, it will work. So that is how we have designed it. Okay. So up to this, these are linear regression. I'm going to Cauchy. Other than that, we have implemented Cauchy prior, we have implemented t-distributed prior, and we have implemented horseshoe prior, which is the most recent prior as well. So this one, if you run it, horseshoe prior, generally you need to run it for longer period. You can see, yeah, no, but fortunately it has converged all of them. And horseshoe prior, for each beta, they compute a corresponding scale parameter. So that makes horseshoe prior more, attractive for many people. They believe that, people believe that it is much more better. Anyway, now I will move on to the logistic regression. In the logistic regression, we have implemented 24 different models. So logic model and probit model with the MLE method of like frequentist method is MLE. And other than that, we have implemented logic model with reach prior, probit model with reach prior, logistic regression with C log link. Okay. Complementary log link with reach prior and Cauchy link with reach prior. So there are 4 link function we have considered and 6 different 6 different priors we have considered: reach, Laplace, Cauchy, t-distributed, and horseshoe. So 1, 2, 3, 4, 5. So 5 different priors and 4 different link function: logit, probit, C log, and Cauchy. So 4 times 5, 20 different Bayesian model options you have. So here is the model definition. So y follow Bernoulli distribution, like it will take 0, 1, and then with the probability p, 1 with probability p, and p is then is some function of xi transpose beta, and alpha is the intercept parameter. So in the R data set, there is a GLM package. In the GLM package, there is a turnout data set. So if you run this, you will get the glimpse of the data set. So the race is one of the thing, age, education, income, and vote, whether they have voted or they have not voted. 1 means they have voted, 0 means they have not voted. Okay, so we want to model vote as a function of age, race, income, and education. Okay, and then this is the data frame. And then logistic regression, I'm just calling it logistic regression, and the logic link. And I'm saying nothing more. That will run and give us maximum likelihood estimate for the uh, or MLE estimation or logistic model implementation for the logic model. Similarly, you can do the probit model. So you have to class is logistic, same model, exact same data set, just logistic regression. But instead of logic model, I'm running it probit model. Okay. So if you done that exact same thing, if you'll see that, not much differences in the coefficient, a little bit differences in the coefficients are coming. Thank you. And then you can do the same things using, now here up to probit model, everything is same. You can see up to probit model, everything is same. Then after that, I'm just giving reach prior. Okay. If I do that, then it will run and it will give you the reach prior estimation. So just a minute. So logistic regression implementation sometimes take a little bit time. Okay. So you can see the same way, you can see the estimates of the intercept and the other variables, the other predictor variables. And so this was age, race, income, and education. So this is age. So age does have an effect, clearly. Race does not have any effect. Age, race, income has an effect, and education also has an effect. So other than race, not all of them have some effect in using the simple reach prior. Now within probit model, reach prior, and all these possible combinations we have implemented. So I'm not going to run all these things. It will be very tedious and very boring for you guys. But you can see that lots of model choices are being available to implement and all these things. So negative binomial regression we also have with MLE, reach prior, Laplace prior, Cauchy prior, t-distributed prior, and horseshoe prior. So all these things are available. And on the top of that, Poisson model, regression model are also available. So Poisson regression model, again with the MLE, maximum likelihood estimates, reach prior, Laplace prior, Cauchy, t-distributed, and horseshoe prior. For different implementations are all available. So now, so this is what we are doing here. In addition, I'm going to show you the CRRao package. Anybody interested can contribute. If you want to contribute, it will be really nice. So here is right now, it is 4 of us are actually holding up the Canon. So now it is latest version is 0.1.1. So we need to, so this is stable actually. So we will update that. Some the README file is not being updated. The stable version is 0.1.1. So if you just use package.add CRRao, it will automatically update the 0.1.1. We will make that corrections. Here is a comparison I think we have. Performance gain. When we did it in R, so we fit this model, LM, MPG, HP plus weight. On an average, it took about 380 microseconds. In Julia, we did it, it is about 127 microseconds. So here it is. Yeah. Julia took 160 microseconds. And then, yeah, this is mean time. Mean time taken is 160 microseconds. In R, it is 380 microseconds. In Python fit, it took 560 microseconds. And in Python stats model, it took 2100 microseconds. I don't know why stat model was so slow, but sklearn is pretty good, 560 microseconds. So one reason Julia is very fast, as I said, it is a compiler language. Because it's a compiler language, it's very useful now. Now, you can say 160 microsecond and 380 microsecond doesn't matter. It is half of the time, but it is still a little less than half and less than 1/4 of the sklearn. Why I bother? If you are working with, a very large data set, it's a very small toy data set. If you're working with a large data set, and if you are working in a, say, cloud server where like typical AWS Lambda, where computation is money. Essentially, if you run it for 1 hour, it will tell you, okay, you pay me $1, and if you run it for 2 hours, it will tell me you pay me $2. This is the kind of model. If you are working in environment, Julia will become very handy because it's a compiler language. You will be able to save some money if you're running it in a cloud server, computation-based cloud server. If you have a dedicated server, you don't have to worry about it at that time, because but still it will, if a very large data set, it might be somewhat effective. If it will be productivity enhancing, I would say. So this is an advantage that you have. And then let me show you some of the code that we developed. So this is the source code. If you go to the frequentist, Bayesian, say this is my linear regression. So this is the documentation, and yeah, that's how we wrote the code. Fit formula is a formula term, is defined as a structure, and data is a data frame. Then sorry, there it is. Yeah, so this is data frame, linear regression, and then prior is also a structure, and then you have to give a h, and then the simulation size, and that's how you define the model. Okay, you can see, you can literally beta follow this, alpha sigma follow this. So we can literally define the model that we want. And then let me show you how, if you want to say, suppose you want to change, I want to try some changes. Okay, so let me just copy this and go to CRRao, this package. Let me create a thing. And so okay, now so what I will do, Okay, let me just do one thing. Let me just take this part. No, not turnout. I'm running the miles per gallon data set on this. So miles per gallon data set will be this one. Okay. And then what I need to provide X and Y. So this is my, oh, I need a Turing also. Turing. Okay. And Turing and random. Turing and random. All right. And then I need this one to provide. Just a minute. Okay. I think I'm done. And DF. Here I have to pick DF. Here I have to pick DF. That's it. So let me explain you what is happening. So I am calling the packages. I'm reading the data frame. Okay, you can choose any data frame. Here I am setting up the model. Okay, here I am setting up the model. I will say I will provide you the X matrix and the Y matrix. And P is equal to basically number of parameters, number of predictors you have. Here 1, 2, 3, P will be 3. Now A naught, B naught I'm providing here. Actually H also, I have to provide a H also here. 0.1. And then I'm saying that, okay, normal follow X beta sigma. And then beta follow normal 0, nu sigma, sigma follow inverse gamma, nu follow inverse gamma. And then that's it. Pretty much I'm running it. If you run this, and then what is happening? Okay, let me just do one thing. Let me just compile it here in this, and here. Oh. So I need to separately install the Turing. Okay. I think I have, I don't know. Yeah, it is run and done. So let me just delete this part. And now if I'm running this, so you can see this Y is this vector and X is this vector essentially, or you can see the Y is like this and X is this matrix. Okay. So I'm saying that I will provide you the response matrix and the response vector and the design matrix or the predictor matrix. And then what I'm going to do, so I just form them and then all I have to do just run the chain. So let me just run the chain. So instead of, I have to give the linear regression. Here I have defined the linear regression. NUTS is the Hamiltonian, the NUTS is an algorithm for very popular Hamiltonian Markov chain Monte Carlo algorithm. And I'm saying that, okay, 10,000. Now run the 10,000 simulation and it gives me the estimates. Okay. So now if you want to change, say, no, I don't want inverse gamma, I want gamma. Fine. You just go change it. And I want sigma to be gamma, not like, generally we don't use gamma, we use inverse gamma. But if you decide that, no, I want gamma, fine. You go and change your model and run it again. And okay, R hats are all close to 1. It has converged and nice. You got a different estimates, right? In fact, you got a very different estimates in this case. So maybe you need to run it a little bit more. I don't know. 50,000. Even 50,000 is very fast, to be honest, the way it is running. Yeah, it is giving very different estimate for some whatever the reason. But it is saying it has converged, but it is giving very different estimates. But anyway, you can try it out and you can see the way I can define my model. This X beta, literally I can write beta as beta. I can literally write sigma as sigma. Literally I can write. So this gives me a very strong, intuition. By the way I write my mathematics equation, I can literally write my, my code in Julia. So the way I write it in board, almost like that, I can write it in Julia. This is what I felt very, very attractive feature of Julia, which I don't get in R or Python or MATLAB. So that makes very interesting to me. So with that, I will stop here and I would be happy to answer any of your questions that you have.
Yes. Thank you, Professor Das, for taking time out of your schedule to speak. So, going over to the audience, do you have any questions for Professor Das based on his talk? Okay, so I have a question is if you don't mind that can this CRRao.jl, this package that you are developing, can it be used for hypothesis testing and other equivalent things
So
in
okay, CRRao.jl, we were thinking to develop it as a sort of a wrapper package, right? You develop a nice integrated package and all. So there is we are thinking of hypothesis testing can be integrated into the CRRao already. There is a package called hypothesis testing in Julia. So, and bunch of like I think 200 plus different hypothesis testing are already part of that package. So we were kind of not sure whether we should integrate that package into the CRRao or not. But yeah, if we see there is a lot of requirements, a lot of people are asking us that we can they would like to see the hypothesis testing as a part of the. So hypothesis testing is a separate Julia package. Okay. So you just all
yes, yes.
yeah, so we can integrate it inside CRRao, or I mean, like it will make it a bit heavier, we feel. It is already there. Are we contributing it by integrating it into the CRRao? And most of my colleagues were saying, no, we will not actually provide any value or service by integrating it, because it's itself a very standalone. More than 200 plus tests are already being added. Very exhaustive list of tests are being added. Some of the test do give a little bit of problematic answers in terms of providing test statistics. So we raise issue with them. So that is always part of the any software development. You find some bug and all those things, and you report, and people go and fix those things. But overall, it's a very fantastic package. I think you can use that.
Okay, thank you for and one last question from my side is what can we do about like when we are analyzing time series? Like still can is CRRao.jl still like good like can it be like applied
Yeah.
for time series
So
analysis?
yeah, right now our plan is to integrate. There are some of the time series development. Let me share my. So if you go to CRRao, can you see my code? Can you see my
Yes.
yeah. So if you go to issues, so yeah, integrate ANIMA with CRRao is one of the do list that we want to do, but it is not being done yet. It is there is in fact if you go there, so there is a nice package called state space models.jl. Okay, if you go there, it's a very nice package already there. This package is very nice package. It is being developed by Julia Hub. It has exponential moving average, smoothing, unobserved component smoothing, Sarima model, all bunch of models are being already part of it, and they are doing pretty good. So we were thinking like, can we integrate this to, so I already give how it should look like, you know, this is how it should look like, and then the model should look like this, like you should take the log passenger. These are the typical uh, automatic forecasting that it should have done. There is the paper I have provided. Somebody has to pick it up and work on it basically. So yeah, I can do it, but I'm just getting bogged down with so many things. I'm just getting, but if anybody wants to try to develop and contribute, it is very easy. At least if you develop the first code and submit it, we can then help you out how to integrate with it. Yes, this is as a part of do list for sure.
Okay, okay. Thank you. Any other questions from the audience? Okay, so I think there are none. So
Okay.
thank you, Professor Das,
You're
and I want to
welcome.
thank you for this wonderful talk on the CRRao package. And is it like it's still in a pilot stage, right? Like it's as you said, it's not still yet fully developed.
So I would say that definitely at a regression, the regression thing is done. We are done with the regression, so you can use it. But we have a plan to integrate, as I said, the ARIMA, the time series, at least the ARIMA model we want to integrate, and we want to integrate the Gaussian process, because Gaussian process there is already a very good PR is being done, and with a student from IIT Jodhpur, she developed the entire Gaussian process thing, integrate it nicely. We have to just do the code review and pass it through. Once it passed the code and test, then we have to test it. Then it will be get integrated into the CRO. So that process just needs to be completed. And obviously, time series is another thing that we want to do. At least definitely the ARIMA and SARIMA model. But anybody can at least CRO. They can start if they have only mainly the generalized linear model framework. They can with a lot of different Bayesian prior they want to try, or the different log functions they want to try. I think we have the most exhaustive list of regression models that we have covered. I don't think any other package in R or Python has done this kind of exhaustive list the one we did. And we able to do that because our Julia is very easy to implement. The ease of implementation in Julia is that is what helps us to develop this package.
Okay, 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 okay. So thank you, Professor, for
Thank
uh,
you very much.
for accepting our invitation. So with this, I end the first talk of Curry Leaf Days 2024. And Chaitanya, can you please tell when the next talk will be, from
Yeah.
which time? Can you please announce it?
Yeah, the next talk is at 2 p.m. You can join via the same link. And before we disperse, I would request everyone to turn on your camera if